You can find us online at rce-cast.com. You can find the links to the blogs, the Twitters, the entire back catalog of every single episode we have ever done, in which we now have more than 100. Once again, I have here Jeff Squyres from Cisco Systems and one of the authors of OpenMPI. Jeff, thanks a lot for your time.
Hey, Brock. It's always good to do another podcast. We've been a little slack recently, so good to get back in the groove here. We got this one up today. We got a few more queued up, but it's getting into the busy season for HPC.
Yeah, so we have supercomputing coming up in November, so we're at the very end of September here. So we were only about a month away from supercomputing, a little more than that. I will be there. University of Michigan will be having its joint booth with Michigan State University again this year. I will be floating around there and floating around other places. Jeff, Cisco always has a booth.
Yeah, we have a booth. Unfortunately, we have a fairly terrible position on the floor this year due to some silliness, but we'll be there. I got my normal OpenMPI State of the Union BOF with George Basilica, my co-host, another one of the OpenMPI core developers. Also helping out with a libfabric tutorial. Libfabric is the new up-and-coming low-level network API. We got that on, I believe it's Sunday. It might be Monday. I'm afraid I don't remember offhand. But yeah, those are the big things that I'm doing at Supercomputing this year. What else you got going on?
So what we've got going on is we will be announcing a couple of interesting things that we got going on at Michigan that you can come by and talk to us about at our booth. We have our new Institute for Data-Driven Computational Physics, which we recently got funded to create. But the big thing that's going on is the new Data Science Initiative coming out of the University of Michigan. This is going to be really the kickoff event for the Michigan Institute for Data Science. We're going to be creating a graduate program, which we already have students enrolled for the fall. And the university is investing about $100 million, and we're going to create 35 new faculty positions. We're putting up a bunch of medium and big data infrastructure, which is really kind of stretching the sorts of things that we've traditionally done here at Michigan. And we're really excited about some of the things we can do. We're already getting our health system lined up for health data. We've got transportation data. We've got all sorts of crazy things going on. We're going to try to bring it all together and look at finally filter through all this data. So come by and talk to us about that.
$100 million.
Right. It's real money. Real money.
Real money. All right. Well, what are we talking about today?
So today we're going to be talking about something that I know actually very little about, and I hope to get some clarification about my understanding of this. We're going to be talking with a researcher who's created a piece of software called Conduit. So why don't we have our guests go ahead and introduce themselves?
Yes, hi. So I'm Cyrus Harrison from Lawrence Livermore Lab, and I'm known primarily for my work on Visit, which is an open source visualization tool, but today I'm here to talk to you about Conduit, which is a smaller effort we've been working on for the last few years.
So can you give us an idea of what Conduit is?
All right, so Conduit's something we've been looking at to sort of simplify our daily life and data exchange between simulation codes, as a whole. So people who write big physics simulation codes, they usually have to deal with I/O and deal with mesh-aware I/O, for example. And there's a lot of pain in dealing with static APIs and things of that nature. So Conduit was designed to sort of tug at that and make things a little bit easier with respect to passing data to and from, say, a visualization tool and a simulation code.
So this was a little bit confusing when I was reading through stuff. A name like Conduit almost sounds like it's a communication or some sort of networking thing, but then you talk about describing data structures and stuff, and you talk about communicating between other things. Can you get a little bit more clarification? Is it one? Is it the other? Is it both?
It's both. So at its core, Conduit is really just about describing hierarchical data. So the best way to think about it is sort of if you cross, JSON, JavaScript object notation with NumPy. So NumPy has been used very successfully in the scientific community, the scientific Python community, for describing arrays and operations on arrays. And JSON's been used for dealing with hierarchical data structures and all kinds of data exchange on the web. So at its core, Conduit's about describing things in core, so in your memory. And then on top of that, you can build services like communication or I/O or serialization.
All right. Due to unforeseen technical difficulties, apparently the internet fell apart in California. So we had to call Cyrus back in on a regular old POTS phone, and We will now return you to your interview already in progress. Okay, so Cyrus, you said something a second ago that confused me a little bit. You said you talked about how static APIs were bad, and assumedly that is in contrast to dynamic APIs. Could you explain that a little bit further?
Yeah, so I guess in a lot of other areas like web development or even in scripting languages, people are used to having a lot of flexibility with how they describe data, how they pass things around. And in HPC, typically, we have a lot of pre-existing APIs for, say, describing what a mesh is or something like that, or we try to solve the problem with code generation. So we're building a big code. We have code generation that describes our complicated objects. And the problem with code generation is that while it gives you good performance, it becomes software engineering-wise pretty burdensome. So if you look at a tool like Visit, if we were to accept code-generated stuff from all the different codes that we want to read in to visualize, it would be really an unbearable process to get all their code and coordinate their own code generation schemes. So when we're talking about this stuff here, we're really not talking about how static and dynamic are mortal enemies. They're just different benefits to doing a dynamic approach. And by dynamic here, I really mean runtime. So you can do full description in runtime and have introspection and things like that.
So can you give us a little bit more history about how this came about? Was this trying to solve the needs of a specific code, or in that code, Visit or some scientific code, or is this just a general problem you keep running into?
Yeah, so it started out with some of the pain points with describing. So with Visit, we deal with mesh data, and we use VTK, for example, for describing our meshes. There's a lot of other things, though, that go along with it that are a little bit more complicated, like in a distributed domain parallel context, how those meshes on all the processors connect to each other, for example. This is hierarchical data by nature. And we have different probably 10 different mechanisms for doing this in Visit. And some of them use packed binary data from specific codes, and some of them use APIs that were specifically designed to deal with this, but then we'd find, oh no, we have one corner case that kind of undermines our whole API. So what we were trying to do is we're trying to let the simulation code describe this data structure to us and have enough introspection so when it gets to Visit that we can actually pull out, the pieces and get what we care about and what we need. And that's where it started out. And it's also an important aspect of trying to deal with sort of in situ visualization, where it's easier to pass things zero copy, like a mesh zero copy from another code. So a lot of jargon there, so I'll let you chase me down on those things.
So you keep mentioning, this is really for, a tool like Visit to be able to kind of, figure everything out on its own. I don't necessarily want to go all the way to saying self-describing, but it sounds pretty similar to that. Is this already in Visit today? Like, is there a version of this in Visit today?
So it's not released in Visit yet, but what we've done, so again, this project started in 2013, and actually over the last year, we had a set of students from Harvey Mudd College working on it with us, where we used it to replumb aspects of different simulation mini-apps. So these are common proxy applications that are used in procurement instead of just regular benchmarks. So what we did is it was pretty interesting. We went in and had the students kind of replumb the I/O, replumb the MPI, and replumb from collecting performance data from the simulations, all just using Conduit, which is kind of a simple building block. So we did these experimentations, and that gave us the confidence that, hey, this is going to work well. So now we're starting to figure out how to roll it out in Visit and solve the specific problems of the code we were looking at starting a couple of years ago, and then also expand it out to be used for lots more things, I think.
Well, let me ask you then about, Brock was just asking you about self-describing, and you were talking about the APIs describing them and so the data itself and so on. These are also terms that are typically bandied about in the current hot sexy of unstructured data and big data and things like that. Is this related to that at all? Because you've also been describing this in a hierarchical type of description, which implies more regularity, that you could potentially use a much smaller description to describe a huge amount of data. Is this the same kind of playing field?
So I think it could be. I think the focus we really had, though, here was on numeric types. So that's why I talk about